Good morning, everyone. Thank you guys for all coming out here. Thank you to Chris and Russell, Keith McGee, and the AV team and all the organizers who make PyCon AU possible. This is really fantastic. I am so very excited to be here. Like Chris said, I write a lot of open source Python software, and I try to give back to the community, and I work at Rackspace. Thank you to them for sending me out here. We opened a data center in Sydney not too long ago, so if you're interested, come talk to me about that. Before I sort of get into the meat of the talk, I bring word on behalf of the Python Software Foundation. We are so excited to see PyCon AU again and growing this year. It is absolutely fantastic to see hundreds of Pythonistas gathering from across the globe here. Super exciting. For those of you who don't know, the Python Software Foundation is basically the fundraising and the legal arm of the Python community. We're fundamentally here to try to enable you and the rest of the global Python community to do amazing things and to try to represent the community as best we can. We are not the developers of Python. We're not the developers of CPython. We don't write the fantastic software that we know powers all of the great work that you guys do. We don't, frankly, do a whole lot ourselves. We mostly try to empower you. We run PyCon US, and we host the python.org infrastructure, but mostly we try to empower you and everyone else to do fantastic things. So show of hands here. How many people knew what the PSF was before I started speaking? And how many people are PSF members? And how many of you consider yourselves to be members of the Python community? Okay, all the hands should be up. If you're coming to a PyCon anywhere in the globe, you're a member of the community. So one of the things that we've noticed over the past years is that there's been a growing disconnect between people who are members of the Python Software Foundation and people who are members of the Python community. And so we're currently in the process of changing up the membership model to get more people involved. Right now the membership model is exclusively you're nominated for membership by an existing member, and we're going to be shaking that up. So going forward, there's going to be three types of members of the Python Software Foundation. They're going to be sponsor members, which are corporate members, which is similar to what we have now. So a company can become a member by financially sponsoring the Python Software Foundation. Fellows will be similar to the existing membership. You'll be nominated for that, but for technical excellence, whether it's writing software, writing documentation, growing the community, anything like that. And finally, supporting members will be members of the community at large who nominate themselves as being interested and excited about helping grow and advance the Python community. So I'm hoping we'll be able to see many of you become members of the Python Software Foundation. We're really excited about this change and growing and making the Software Foundation more inclusive. And to that end, it is our goal to build the biggest, best, and most open Python community we possibly can, to open our doors to as many new people, whether they're new to Python or whether they're new to programming entirely, and to continue to have the technical excellence we know that is a part of our community today. Effectively, our goal is to have continuous improvement and continuous deployment for our community. We think we've done a lot of good work to this point. We know we have a lot more work to do to be as fantastic a community as we can, and I hope you'll all be a part of that goal for us. If you look at the work we've been doing over the past several months, in past, most of our grants went basically towards conferences, other Python conferences. We've expanding those more and more towards education outreaches, more focus on growing the community, diversity, basically looking towards not just having a great Python community today, but for years and years to come, and we're very, very excited about this. Finally, PyCon 2014's website is now live. We're hoping many of you will be able to join us. It will be in Montreal in April next year. The website is live. The call for proposals is up. We hope you'll submit fantastic talk proposals as you have for this conference. And with that, back to the actual topic of this talk. So this is a picture of me and my best friend. I want to say we were about 8 years old at this point. And about a year ago, I graduated with a degree in computer science. And this year, he graduated with a degree in computer science. We both work as programmers, but his degree is in engineering, and my degree is in science. And this sort of led me to thinking about what it is that programming and software engineering, software development, what are we doing as an industry? What is our function? How are we similar to other industries? How are we different from them? And what can we learn from them? And so I started looking at what other types of industries there are and how we're similar to them. And the three that I came up with are engineering, science, and art as sort of three broad areas of inquiry that have some overlap with what we do as programmers. And it's my hope to learn from them because programming is an incredibly young profession. At the absolute oldest, we could say we're maybe 70 years old, and in practice, we're 40 years or maybe even younger. And I don't think we're particularly good at writing software. And we have a lot of problems, and so I want us to learn from these more established professions, and I want to learn from them because they seem to have ways of solving problems that are interesting and possibly useful. And we have a lot of issues now we write software. So software has bugs, lots and lots of bugs. About half the time when I take my computer out of sleep, it immediately goes back to sleep. I mentioned this to someone the other day and they said, yeah, that happens to me too. And if I were a normal person, I would probably think, wow, computers are terrible. But because I'm a professional software engineer, I can say with definitively, computers are terrible. And we're not really good at doing this. I imagine every single person in here who has shipped a piece of software has shipped some awful bug. I know I've shipped many. NASA actually came up with a methodology for how to ship less bugs, which is an important thing if you make a spacecraft. And basically what they were able to do is by incredible levels of manual review and automated review and more than an order of magnitude cost increase to develop software, they were able to actually get things down to basically having no bugs. Software's slow. Moore's law says that the number of transistors we have available will double every 18 months. And in practice, over the course of my lifetime, that means computers have roughly gotten 16,000 times faster. And they don't feel any faster at all. Every resource that the hardware engineers seem to give us, we seem to squander away. And I think this is, again, going back to we don't know how to best make use of the resources we're given. And we're also really slow to deliver software. Or maybe not. But we're definitely terrible at estimating how long it'll take us to deliver software. There's a fantastic write-up someone did explaining why this is. And it goes, imagine you were you lived in San Francisco and you wanted to visit your friends in LA and you decided, we'll hike there. It's about 400 miles. And so you say, okay, 400 miles, we can walk 40 miles in a day. So it'll take us about 10 days to walk from San Francisco to Los Angeles. I think it's about the same distance as Melbourne to Sydney. So doesn't sound particularly realistic, but like the math works out. You walk 5 miles an hour, you walk 8 hours a day, you'll get there in 10 days. After a day you start walking and it turns out you're not exactly walking in a straight line. It's not quite as short as you thought it was. So, we'll double the estimate. We say, okay, we're not gonna make it there for next Saturday, we'll be there a week later. You walk a little further and it turns out the terrain is really rocky and now suddenly you're walking at a third the rate you originally did. So you call up your friends and say, it looks like we're going to be a bit longer. We'll push our dinner back about a month. You keep walking and you start getting some blisters. You have to take a day off from walking. And suddenly before you know it, your estimates make no sense and that's about what we're doing when we're writing software and trying to predict how long it'll take us to ship. We say, we've got these 3 features and they'll take a week to develop. We'll ship this in 3 weeks. And I think we can probably do a bit better. So my conclusion was, I don't think we know how to build software. We don't have a good methodology to it. We don't have a formula for how we do it the way I think other industries do. And I don't think we know how to design software. Because I know when I sit down to write some software, I take this description of a problem and I scribble on paper for a bit, and usually I get annoyed because I can't write very legibly. So then I type for a bit, and then I start actually writing some software. And there's no process to it. Things occur to me and I type a little, and sometimes software comes out. And I don't think this is a real great methodology. It sounds less like a professional industry and more like a comedy sketch. Because I have no idea what I'm doing. Step to step, I'm just making it up, doing whatever seems naturally, and sometimes it works, and sometimes it doesn't. And at the very minimum, I'd like to be able to explain what I do, because when I work with a friend or try to teach someone how to program, I'm really bad at explaining my process, and that makes it really hard to teach people what I do. And that's really unfortunate. So I started looking at how other industries work. So engineers do applied science. They deal with materials, structures, and physical systems, and are said to be the intersection between science, technology, and society. And what we do is kind of like them. We build stuff for some definition of build and some definition of stuff. And their methodology is based on taking existing fundamental sciences and applying them to building things that work in the real world. And I don't particularly feel like what I do is an application of science. When engineers work, they might build a model of the world and estimate, here are the forces of physics that will apply, and this is how gravity will come in. And so we'll build a bridge based on modeling out, these are the types of materials and these are their strengths. We don't tend to do that so much. We scribble on paper and say, I guess we'll maybe have about this much traffic, and hopefully we'll be able to stand up to it. Not, well, this bridge is 80 meters across, and so 7 cars can fit on it at once, and they might weigh this much, and so it needs to be this strong, and we need 10% leeway. We don't have the same sort of rigor that they seem to apply to building things in the physical world. And I don't think that's because we don't build things that aren't equally important. We may not build bridges, but we build all sorts of other things that are sort of life-threateningly important, and so I'd like to apply some amount of rigor to what we do. Science, of course, is backed by the scientific method, which is a process that's been honed for 300 years, which we have, I don't think, anything like. And the objective of science is to develop a fundamental understanding of nature by performing basic research. It was funny, when I graduated from school, each of the departments introduces all of the graduates, and so and they say, this is what this department is about. So the architects, they said, these are the architects, they will design the world, and the engineers, it was, these are the engineers, they will help build the world, and for the scientists, it was, these are the scientists who will do science. And I don't feel particularly like I'm doing science most of the time. Everything I studied about science says that you develop a hypothesis, and you do some existing research, and you test your hypothesis, and you do statistical tests on the results to see if you actually produce something of any value. And I don't see any of that going on in our industry. And I tried to get a good definition of art, and I failed miserably. And then the other day I went to MoNA, the Museum of New and Old Art, and now I really have no idea what art is. But it seems to be a profession that's not unrelated to ours. I think many of us, particularly in the Python community, care a lot about the aesthetics of our code, care about things that we can't quantify precisely. We can't say how readable code is, but we know it's important. We can't say really how easy it is to write code, but we know it's important. And we care about beauty in a really interesting way. So I think we're doing a little bit of art. And so there's this thing called epistemology, which is basically the philosophy of knowing things. How do we know when we know something? And I'm sure there are actual philosophy majors in the room, and I'm butchering this horribly. But this tries to answer questions like, how do we know that the sky is blue? Well, okay, we have these premises, and what system do we use to go from our observations, to go from rules? How do we know that we've reached a valid conclusion? How do we know the things that we think we know? And for us, that means, how do we know that our programs do what we want, for any value of what we want, that it serves the customer's needs, that it won't break in certain ways? Any of these questions. I think some common answers to how do we know our programs do what we want. Oh, I ran it and it worked. I looked at the output, it was great. Maybe you've got some tests, or my personal favorite is, we have millions of users and no one's complaining, clearly it works. This is a really popular one. And so to answer that question, I started thinking about what makes programming really, really neat. For a while, I thought I wanted to be a hardware engineer, and then I actually played with some electronics and found out I have absolutely no interest or aptitude for it. But programming, which sort of looked kind of similar, just appeals to me in a way I can't imagine. I started looking at what are the things that make programming really, really cool, and how can we use them to develop a better understanding of what we do, and how do we take better advantage of them. So the first thing I found that was really fantastic is we can isolate fantastically. We can put our programs in boxes and look at what they do, and we can remove any external factors. Anything we want to do practically can be run on our computers. You can put a simulation of a bridge on your computer, but you can't put a real bridge in your lab and play with it. We can put our programs, almost whatever they are, on our computers and test them, and that is fantastically interesting. Our programs are composable. We can take any two programs practically, and through horrible messes, no doubt, but we can combine basically any two programs we have, and just looking at the Python package index or any code base I've looked at is a testament to our ability to pull together code bases from people who've never met each other, who have totally different interests, who have never thought about the same problem for even a second, and yet we're able to work together and put our code together. And I think that's really fascinating, because that is definitely not something that I think other industries have. By and large, you can't put two paintings next together and say the result is art in the same way each of the individuals is. But we can put two programs together and say the result is a program. And finally, we have the ability to observe what our programs do. We can instrument them, find out exactly what they're doing. We can look at what they print out. We can put them totally in a box and look at what network packets they're sending out. And we can do this all automatically. And I think this is super fascinating, because a rivet can't tell you when it's bending under too much stress. But a component of your software can tell you when it's falling over. So, given all of these, how can we better know what our programs do, and how can we better take advantage of this? So the first thing I think we can do is we can double down on testing. We put our programs in boxes, and we can observe exactly what they do, from the smallest little functions up through giant systems we've built. And the computer will tell us when our program is wrong. And I think this is actually a really interesting divide between things that you can tell when you get them wrong right after you've built them, and things that you don't. And the more we can find to know when things are wrong very early, the better. I believe things like security are really hard, because you don't know that your security is broken until someone breaks it, for the most part. We can tell if most of our programs are broken because we have a desired input and a desired output, and for most of what we do, there's no sort of complex side properties like no one can tell what this encrypted value is. You can't really write a test that says you can't reverse this encryption. You can write a test that says this function will return 42. And that's something we should take advantage of wherever possible. And I don't think there's really any analog to this in other industries. We can do benchmarking. We can figure out how fast our programs go. And I think we can start to apply some of the scientific methodology to this. I want to make a change to my program. I want to know if it produces a result, if it makes the program faster. I can sort of take the fundamental tenets of the scientific method. I can isolate my change so that there's one independent variable we're varying. I can do statistical tests to see if I really produced a result. I can try to actually do some science with this, and this is fascinating. This is part of why I love working on performance, is the ability to quantify the changes I've made and actually look to, really verify that what I've done has made a difference. We can use logging and metrics to know what our programs do, what they're doing, how frequently they're doing, how quickly they're doing, and we can reproduce the fundamental steps of our programs, the steps that they took, and see where they went wrong, what state something exactly is in. We can use all of these tools, and Python is better than almost any language in this regard, because it gives us incredible introspection facilities for us to find even better what our program is doing, what state it's in, and how various things look. And I think we can apply the scientific method even more, not just to benchmarking, to making other changes. From a certain point of view, a test-driven development methodology is sort of a very quick, very sort of reduced scientific method. I write a test that's my hypothesis, or that's my question. Can I produce a function that has this result? I make a change. If the test passed, my result is confirmed. If not, my result was not confirmed. That change does not produce the result. I think if we start thinking in these terms, we can be a little more rigorous in how we write software and maybe produce slightly better results. And we know that this has produced very good results for another industry, so I think it's at least worth trying. So I think programming is a lot like other industries. We build stuff like engineers, we can observe results like scientists, we care about aesthetics the way artists do, and so I think we need to dig more. This was, in many respects, a very surface level look at what these other industries do. People who I think, frankly, actually practice these industries on a day-to-day basis, as I'm sure many of you do, or you work with people who do, they can teach us a lot more about what we can learn from the methodologies of these industries. But programming is also not like other industries. We have lots of very neat, very special things that computers enable us to do, and I think we can take better and better advantage of them. The fact that everything we do on a computer can be observed by the computer is just a super fascinating process that I still struggle to get my head around, but just seems to be such a powerful thing that my computer can tell me when the program on the computer works or doesn't work. And I think we need to get better about teaching programming. If you look, most people who want to program for a living take a degree called computer science. Computer science is a wonderful thing. It's very fascinating. It is incredibly practical and research-oriented and everything else, but it's not the same as programming, and being a good computer scientist is not sufficient to be a good programmer. And being a good programmer, of course, in no way indicates you know anything about computer science. And so the average computer science curriculum that I've looked at looks like you learn a bit of programming, and then you learn a lot of sort of theoretical things with some practical application, data structures and type theory and algorithms. And then you spend maybe a semester looking at some practical software engineering, some design patterns. And then we send you out into the real world to learn to actually write software. And that doesn't actually make any sense to me. If I were designing coursework for a software engineering degree, I think you'd spend a month talking about the philosophy of logging, how to log effectively, how to log usefully, what the advantages and differences or different approaches are. You'd write a compiler and you'd learn type theory. You'd spend a full semester talking about the fundamentals of version control, because I still don't understand Git. All right, people tell me it's a directed acyclic graph of commits, and I go, huh? And I think you spend a semester learning about the theory of version control. It might actually start making some sense, I hope. You'd build giant programs in a software engineering degree, and I think we need to make a software engineering degree possible. There's a guy named Greg Wilson who's written a book called The Architecture of Open Source Applications, which is sort of an effort in this direction. He's got this hypothesis that what makes great writers great is that they write a lot and they read a lot. And we should probably do more of that for software. We should write more software as a practice, as an exercise, and we should read more great software. So this book is dedicated to looking at large, popular open source applications and what their architecture is. And he also teaches a course called Software Carpentry that's basically dedicated to this idea that we can teach software engineering as a craft, as something we can learn, and not just as oh, well, you're going to take 4 years of theory and your first job will teach you how to program. Computer science is fantastic and it would be a component of any software engineering degree, but it's not sufficient for what I think most of us want to do. So I'm asking all of you to please help me understand what it is I do, to help me better explain the methodology I and we all bring to the software we write, because I don't want to keep guessing at what I'm doing, at what helps me make programs that work versus what makes programs that don't work. And I want to be able to identify this so I can analyze it, so I can teach it, so we can make it more efficient, so we can get much better at programming and teaching programming. Thank you guys very much. Questions? We've got mics up at the front.
Before we take questions, is Chris Bosh in the room? Cool. Can you see me in just a moment? Cool. So if you have questions, there are some microphones at the front of the stage. Could you queue up behind them and then ask your question? Russell, you need to do a lap of the lecture theatre before you can ask a question.
Okay.
That's not fair. So first off, absolute fantastic. Thanks for coming in. Git is very easy to understand once you realise that it's the basic idea is that branches are homeomorphic endofunctors mapping submanifolds of a Hilbert space. So it's easy to understand. Don't worry. It punches you in the face. I've got. My father's a mechanical engineer by training, and so a lot of where I sort of my worldview came from being trained by him as a young guy. But interesting, I've ended up in the computing side of things, not the mechanical engineering side of things. The observation that I've sort of had over a while is that the fundamental difference behind mechanical engineering and what we do in computing is the mechanical engineering, they look at the problem at a much higher level with the benefit of thousands of years of science wrapping the outside bounds of what's going on inside. So that you don't say, you've got a beam with a weight at the end. You don't try and model the internals of the beam and the strength of the beam. You just have a large book on your shelf which says, as a result of 400 years of putting weights on the ends of beams, we know this is the calculation you need to do. In computer science, we're a young profession. We haven't developed that yet. And every time someone sort of tries to apply mechanical engineering principles or engineering principles to science, what they kind of try to get to is the Lego model, where you're going to have blocks which all plug together. But no one's ever really managed to make that practical because no Lego block is ever flexible enough to be genuinely useful. You end up having to tweak it and change it, and that's where all the bugs flip in. So, in your mind, is that an issue with the maturity of the profession, or is it a fundamental difference in the way programs work and the way programs... the problem is so different that it actually requires a different approach?
I think it's a bit of both. I think we could treat, individual components of our software as, completely static things that we plug together using either this way of combining them or not at all. But the nature of programming has given us an incredible flexibility to combine pieces that weren't intended for each other. And so you can see things like this NASA methodology where they're really able to bring these bug counts down to basically nothing because they put so many restrictions on themselves. And I guess I'm dissatisfied with the idea of this many restrictions. So what I'd like to do is find a way to bring those together, to take the flexibility that computing enables for us and combine it with the ability to combine these pieces in ways we can understand. And it's my hope, and I have frankly no reason to believe this is true, other than I have no reason to believe the opposite either, that we can at least do better than we are today.
Really quickly, is Lex Hilder in here? Cool. No more questions?
Yeah,
cool.
We're just not standing up, sorry. Okay, somewhat shorter question. The PSF changing the membership, when?
It is an ongoing process. I wish I could give you a better answer about the process is not yet complete. It is not, unfortunately, yet possible for everyone in this room to become a member. Oh my.
He's not happy.
We will make quite a bit of noise when that change happens. You will... Oh man, no pun intended whatsoever. We will publish it through every channel we can think of when that change is all the way through. It's the best answer I can give you, unfortunately.
Thank you.
Hi. With regards to scheduling and estimates and all of those kind of things, I fully admit that I'm incredibly bad at estimating how long software takes. But I think it's also interesting to look at like construction and large projects like that. I don't know if anybody's actually seen a construction project that's run on time. I don't think there's a lot of them, and I'm wondering if kind of not having an insight into that industry, I wonder if badly estimating time is a human factor, not necessarily a industry factor.
That's a great question. I think it's probably a human factor in some respects. The interesting point for me is the smaller we make a thing, the better we are at estimating how long it is. So I think in certain respects it goes back to what Russell was talking about, in that the way we combine things seems to be different. We're not as good as using the Lego blocks and combining them. And so the more we can break down what we do into the small pieces, the better we can do at estimating. If we look at things as, sort of the giant blocks I think we do today, I think we can see that a lot of the places our estimates go wrong is the integration phase, which is maybe not surprising, the same phase the bugs slip in and almost everything goes awry. If we can, sort of dig down to this, really embracing this small isolated bits and the ability to compose them, I think we'll get better at estimating as a result.
First, thank you very much for your talk. It's brilliant. One thing that struck me when I've done a few software projects with larger companies is that for some reason we keep getting trapped in our own hubris. We say, okay, we've just built this awesome software component that's taken us only 2 weeks. I'm sure the rest of the project is going to go just as smoothly. As you were saying before, the walking from one city to another. At some stage, though, if you keep on meeting the expectations that are pushed on you from above, and you keep crunching hard to get this software out at the time it's supposed to get out, people who are trying to make decisions about how long this stuff takes say, okay, my team are really awesome. They can do this in this much time because that's what they've always done, and they don't see this group of people over here who've been trying desperately to make this stuff work for the last 3 months. Is it a matter of trying to figure out how we actually say, no, we can't do this in this time, as opposed to always that, yes, we can do this, I'm sure we can do this?
It's another great question. There's definitely some we need more just say no to, increasing demands and, demands that are unrealistic engineering-wise. There's a boatload of psychological and sociological research that shows that just throwing more research or throwing more people at a problem, throwing more hours for an individual person at a problem will not produce better results. The flip side of that is, I think we want to continue to hold our industry to a higher standard. We don't want to, push back on doing better, and maybe doing better just means investing 10% more time up front for 40% more time later. A better understanding of this would be very good. We know that things like test-driven development and some other methodologies, they produce actual studies that show that they will take approximately this much more time up front and produce approximately this percent fewer bugs. Looking more at doing more research along those lines, I think, and actually, taking these to heart, not, oh man, they, by working 80-hour weeks, they were able to chuck out this result. How can we just put more 80-hour weeks in? Like, that will clearly produce better results. Yeah. So it's a combo.
Thank you, Alex.
Hi, Alex. I'm Alex. I really enjoyed your talk. So you characterize programming and software engineering as between science, engineering, and art. And what I'm wondering is, if you make it more like engineering, if you do somehow make it more predictable and more reliable, can you do that while maintaining that artistic element, which I think a lot of us enjoy and which actually attracts a lot of us to programming in the first place?
That's a really challenging question. My hope is that they're not at opposite ends of the spectrums. They're much closer together. I think embracing sort of the beautiful code, the very readable code, it's my observation that for myself, the more beautiful, the more readable code is, the better I'm able to work with it and the better results I can produce. And yeah, it's my hope that they're not opposite ends of the spectrum and that they're sort of in many ways one and the same. And I hope I'm not wrong about that, because I very much enjoy sort of the beauty of trying to architect a large system as well. That's an incredible attraction to programming for me. Does anyone else, the mics are up? Or?
Hi Alex, great talk. So taking it back to the context of open source rather than development in general, things like GitHub and Bitbucket and open source repositories tend to be towards the front edge of tools that we can use, and things like Jenkins provide us a lot of information. To what extent do you think that by driving tools like that forward, we can just give people more help? Like people who know things about logging, mean that you don't have to put it in your tests and put the log points in. Maybe the software we have as a community could do it for us.
I think more tooling is absolutely a part of us becoming a more mature industry. Both tooling from the perspective of being able to automatically instrument our code, so it's not the onus of every developer to manually instrument specific things. But also tooling from the perspective of being better able to work as teams and combining the effort of many people. Things like a good code review system go miles to helping multiple people on a team understand a project, to helping people give each other useful feedback. And good tools from this perspective, I think, are very important to producing better results.
Hi Alex, my name's Adam, and my question is a bit more pragmatic around estimation. And when I'm thinking about it, and the problems that I come up with, like, one of them is, how do I define complex risks and like in software and document them to communicate for estimation purposes? Do you have a process or some pointers to be able to?
I don't have a good answer to this. I'm as bad as anyone else. I look at a problem and I say, this will take about a day, this will take about a week, this will take about a month. I have no idea. Things fall into one of those categories is the closest I can estimate, and as often as not, it's completely wrong. I would love to find more and better methodologies for good estimation.
I work at an engineering firm, so we've got a bunch of engineers, civil, mechanical, whatever, and we've got our software team as well. Is it that from the engineering side, they might estimate time to engineer a solution, but they're not the ones that are building it, whereas we are designing, like time estimating, designing, building, and possibly testing others' code, gets reviewed, goes out. So from their perspective, they've broken it up into the engineers time estimating, doing the engineering of it, and then it goes off to the builder to make something of it. And he's got his own time estimates and construction times and all that kind of stuff. So is it that we need to break it apart into, can we, that someone else designs it and then someone else comes along and builds what they've said, and there's different time estimates at different times?
That's a great question. Fred Brooks, the author of the Mythical Man Month, writes about this thing where basically what he identifies as being really important to a successful software project is having a great designer. It doesn't mean graphic or visual design. He's talking about someone who will architect the entire program, see the entire problem space, and design it. And a lot of open source projects like Django have someone like a BDFL or Guido for Python who will sort of set the tone and do sort of much of the high-level design, and other people will fill in the details and implement it. And I don't think that's wrong. We can see that a lot of the systems we like very much are, very much designed by those principles, even if lots of other individuals contribute to sort of the sub-design bits. The flip side of that is, while it seems to work great for open source, anytime I hear about someone who works at a company where there are architects and, developers, and the architects, come up with this plan but never implement it, I've never heard anyone describe this positively. So I don't know if it happens to be that corporations that are organized that way are also bad at writing software, or it doesn't work in certain environments. I don't have an answer to that other than good, comprehensive, consistent design seems to be an important thing, and finding a way to achieve that seems important.
So we'll call this question the last one.
So again, with regard to scheduling and in response prompted by Adam's question, in the psychological literature on human bias, there's something called the planning fallacy, The most famous experimental result there was asking a bunch of university students how long they thought it would take them to complete a particular piece of work, asking them for 50%, 70%, 99% estimates. Turned out that of the 99% confidence level, 45% of the students finished by that time. And so being aware of this bias and repeating the experiment had pretty much no effect. This has been verified for a lot of the bias literature, and the only way that was found to be effective, has been found to be effective thus far, is weighting your estimates based on how long it took last time. According to psychology, it's the only known way to produce reliable task estimates. What do you think about integrating that kind of approach?
Ooh, that's another tough question. I think one of the challenges for us is we as much as possible try to avoid repeating the exact same task, because we're, good software, the old joke, a good responsible software engineer would never write a bomb Baghdad function. They would write a bomb function that takes a city as a parameter, right? We would never, write the same function over and over again. And yes, this is something along those lines is probably right. I fear that it's the differences between the tasks in the same way it's the integration between the components which would be where we screw up. But yeah, I guess practice makes perfect, hopefully. Thank you guys very much.